The next test or process I've chosen with this oscilloscope is a very obvious one, I think: ignition profiling. I've always explained in my training courses, I think one of the most complex parts of circuit evaluation is ignition, because there's an awful lot involved in it. You've got the primary, you've got the secondary, it's about voltage, it's about inductance, it's about burn time, it's about the profile of the ignition event across the spark plug. There's an awful lot you can interpret into it. And it's something, I think, if we go back years, I've been using scope, 35 years. And I'll be honest, when I first started using scopes 35 or so years ago, I was ridiculed by elastomeric scan tool people because I didn't see the future in it. I think events have proved differently, but that's part of evolution. And one of the first things we had to get a grip with was ignition and its performance in real time. So this is what we're going to focus on. To confirm efficient induction and ignition energy, induction is measured in henries. We're not measuring henries, we're actually measuring current flow through the coil, and how that current's being controlled through the coil is very, very important. The skill sets is to set a complex arrangement of parameters: voltage, time and triggering. We're going to use triggering, current ramping, voltage drop on load, and we're going to add the next presentation, which is ground and power checks, as a sequel to this to follow on, because the ignition loading is quite a useful circuit to use when we're looking at voltage drop and the ground references as part of an add-on to this particular test. So that's what we're going to do. So there's a whole range of different adjustments. So I think what I'd like to do first, direct ignition, VAG. Over the years, current has increased through coils from around, well, in points it was 3 amps, then went to about 6 or 7 amps as ignition evolved, then went to about 10-15 amps with introduction of early coil and plug systems, and the very latest, not this one, but the very latest coil and plug systems now have 20 amps running through the ignition primary, so it's increased all the time. We've attached the current clamp to the common power supply. One of the great skill sets, if you like, when you're using sensors and different tools, is to try and capture the information in the best possible place. Now, if you're measuring current in a series of events, if you can measure the current once and then apply it to different components, 4 coils, then that reduces the amount of moving around and connectivity. So that's a common power supply across all 4 coils. I've chosen number 2 coil just because the accessibility is a little bit better. Sorry, number 3 coil on number 3. And the channel 1, blue, channel A, is focusing on the control trigger from the ECU. So I've got the control signal, that's what we're going to actually trigger the scope on, and current. They're the only 2 measurements we're making at the moment. So I'd like to start the car, and then let's begin talking about how I set the oscilloscope up for amplitude, voltage range, time base and trigger. Now this is my home screen. I've deliberately gone back to the house, cleared all the previous settings. The trigger is a 5-volt power on event. So channel A should be set to 5 volts. And you can see as soon as I drop range, you get more noise. Every time you reduce the range, you get more noise. So these events here, which we're going to zoom into shortly, is the control of switching on, switching off of the coil from the ECU. The events down here represents current flow on channel 4 in black, and I'm expecting about 15 amps. Now the clamp I'm using, 100 millivolts is 1 amp, 1 volt is 10 amps, 2 volts is 20 amps, so I'm still going to use voltage as scaling. So I want to set channel 4 at 2 volts, 20 amps, so the scaling now, 4.5 0.4, 0.8, 1.2, 1.6, 2 volts, 4 amps, 8 amps, 12 amps, 16 amps, 20 amps. And immediately you can see that the threshold of current is just under 1.2 volts, 12 amps. Now you've got more current events than you've got triggers because we're measuring current in a common supply circuit. So from a diagnostic point of view, although I'm focusing on one particular coil, I can tell you that the current ramping on every other coil is correct. So I'm already ahead of the game. But there's too much time here. There's too many events. Now, if I was going to look for an intermittent event, I would not use a trigger. What I would do is compress, high sample rate, and use the zoom mechanism to go and find it. Because if you set a trigger, you have to almost predict the parameters of the failure event itself. And that's very difficult in a complex signal. So I try and stay away from triggering. But in order for me to stabilize this event, for close-up analysis, I do have to use a trigger. So what we're going to do is set a trigger to repeat. Every time the trigger parameters have been satisfied, it will update the screen with every event. I'm going to deliberately move the trigger in a bad place. Scope is blind. It's pre-trigger. The scope is blind. The dangers of setting an inappropriate trigger is that the scope is blind. I want to set the parameter somewhere safe, so I'm going to go way up there. I want to set it on channel A. It's currently on channel B, because the event I'm focusing on is on channel A. We're only just clipping it there. I want to bring it down a bit. So I've chosen somewhere unique within channel A to set the parameters. Now I can free to move that triggering point wherever I wish. So let's reduce the time base. Remember I said time base 1 millisecond, 100 milliseconds and 5 seconds. It's an event. So I want to change the time base to 1 millisecond. Boom. I want to bring it. So the threshold has been set. The offset, now I'm going to move to the left. So now you can see the 5 volt trigger event. I could actually reduce that, but let's choose a 10 volt scale. I'm happy with the trigger where it is. Now I'm happy with that profile's better, just sits better on the page for me. Coil on, coil charge, coil off. So the control of current, the switching on and the switching off, current is in black, is achieved by the ECU. The amount of current that flows is the responsibility of the power stage, which is built inside the coil itself, in our case. So what have we gained from this? Well, we need to know what the current flow is, and the current flow is just under 1.2 volts, just under 12 amps, which happens to be correct for this variant of direct ignition. That's how much current is flowing. But we need to look at inductance. Now, if I was to turn the clock back a number of years, we initially managed inductance by looking at the back EMF. Voltage up, current down. You turn a coil on, voltage goes down, current increases. You turn current off, voltage goes up. That inductance used to determine the efficiency of the inductance process. We've now exchanged that in favour of current. So the increase in current in an inductor, a coil, is progressive unless it's triggered by a capacitor, which it isn't in our case. to a certain threshold. How much current is important, but the process of interrupting current is absolutely vital if we're going to create enough energy in the coil to be transferred into the secondary winding producing HT. And that's established by the speed of interruption. And it should be instant, it should be visually within this sort of time frame. With a 1 millisecond time base, it should appear to be vertical, instant. With a little undershoot, which is healthy. So if you actually see a little bit of undershoot, and the more undershoot, the healthier it is. Sometimes it's clamped, sometimes it isn't. But that undershoot is not an issue. And I've just made the comment about it appearing vertical. Well, you know what, if you stretch time enough you can bend anything. And you can see that when you start going into microseconds, millionths of a second, and nanoseconds, you can make the line appear bent. Now, a word of advice, you start to see some very discrete faults with the inductions process when you start looking at this within this sort of time frame. So don't make the mistake of not examining this kind of interruption process. You may have the right amount of current, but if the induction process is in any way becomes faulty, and what I mean by faulty, starts to become rounded. So instead of the power transistor interrupting the current promptly, it starts to become leaky. And if it becomes leaky, you start to lose ignition energy, and eventually you'll have a coil failure. So don't feel afraid of looking at this event very, very closely. Happy with that, it's vertical, it's clean, little bit of undershoot. So the primary sign of ignition, I'm quite happy with. What about the business end, HT? Well, in the past I would have looked in primary, I can't. Primary is completely restricted from access by anyone. It's inside the coil, the construction of the coil itself. So I have to use a coil and plug probe. This is the current modified COP, coil and plug probe. And it can actually be used on anything that creates inductance, whether it be an injector, anything that has a reasonable amount of current passing through it, can actually be used to pick a signal up. Now, it's a fairly generic tool. Now, I don't know what the sensitivity of this device is, so you have to guess what sort of range. Now, I normally say to people, choose 1 volt as a starting point. So if I change, now this is connected to channel 3, the green channel. So if I select 1 volt on the green channel, so the attenuation is a bit of a guesstimate. The higher the quality of coil, the worse the signal, or the lower the amplitude. And these are high quality coils, so I'm not expecting to get a good signal from this. Placing the device, now we do have a signal. You can see now we're looking at the secondary event. I'd like it to be a little bit bigger, so I'm going to reduce that 1 volt to 500 millivolts. And this is where a little bit of adapting of ranges comes into play. I'm fairly happy with that. So what I'm going to do now is move very quickly across there and capture it. Make sure I've got a trace we can discuss. 32 frames of data, so I should be able to capture that, I hope. Yep, just. You can see a slight variation in burn time from one event to another. You know what, I think I'd like that a little bit bigger. I'm going to go down to 200 milliseconds. I'm tempted to say I don't like that. I think I'll go back to half. I'll try and explain my thought process there in a moment when we've switched the engine off. That's better, that's what we want. That'll do. Right, let's switch off. Right. Where shall we begin? Because we've an awful lot going on here, and we're going to add to it shortly as well. Right, the primary event that creates this ignition, let's forget the cam and crank sensors, is a control signal from the ECU. It's a power on signal. When it goes high, current starts to flow through the inductor, the coil primary circuit. Whilst it's maintained high, current's allowed to increase to a predetermined level, at which point the control signal drops back to zero and the inductance process takes place, producing an interruption, a prompt interruption of current, which then creates the inductance into the secondary windings, which have no physical relationship with primary. In close proximity, yes, but there's no connection between the two. The induction process, and this is determined how much energy is created in secondary, is down to what's called a turn ratio within the coil. That's predetermined. We don't have to worry about that. All we have to worry about is how much energy. Now, energy is measured in joules. We don't measure joules. We interpret that as burn time. So the amount of energy created by inductance, that's measured in Henry, and energy in joules, is down to the design of the system. All we need to be sure of is that system functioning normally. So the expression burn time, you guys might call it spark, burn time is a crucial measurement. It's absolutely crucial. You have to know what it is and you have to be sure it's right. If the amount of energy transfer is not right, you won't burn the fuel, you won't create the amount of power the engine should have, and your emissions will suffer accordingly, and you may damage things like the catalyst. So it's that important. Burn time on this system should be around 2 milliseconds to 2.2 milliseconds. And you can see here from this, I probably need to move the cursor, the trigger a little bit, but I can measure it with the cursor. So let's measure the burn time accurately. I can see it's about right, but let's measure it. So this point here represents the start of the energy crossing the plug from the plug electrode. That point there represents where the energy can no longer cross the spark plug gap and inverts back into the coil, creating this, what is called ringing. Now we'll come back to that, that's very important. But the burn time, number one with ignition, 2.118 milliseconds. That, guys, is absolutely spot on. So number one is burn time. If burn time is correct, there cannot be anything wrong with the energy released from the ignition system. Be careful what I've just said. The energy is represented by burn time, but I did not say it guarantees the correct delivery of that energy, because that energy could actually be jumping across somewhere else and not going across the plug. The statement I made was the correct energy conversion is represented by burn time. If it's not, the second most important, so there's four things you need to look at: burn time, current in primary, firing line voltage and coil ringing. Four things. We can only measure three with this system, but 3 out of 4 is near enough. Burn time, number one, always. Number two, current in primary. If the burn time's wrong, is primary correct? Primary is represented by current. Amplitude, about 12 amps, yes. Inductance, prompt, with a little bit of undershoot, yes. Inductance is good. Good burn time guarantees good inductance. Good inductance does not guarantee good burn time. What happens here to the left is primary. What happens there to the right is secondary. And that determines how you apply the scope to prove exactly which part of the ignition circuit is responsible for the fault. Is it to do with control, primary, or delivery, HT? So we have a good burn. Coil ringing. I mentioned four things, I said we can only measure three. Coil ringing. The resonance created in the inductance, in the coil, is represented by the voltage going around the coil with no access to ground, becoming weaker, creating heat in the coil, And it should represent itself as this smooth ripple effect. It's like a cone. And that is a beautiful ring. If the structure of the coil, this is secondary we're looking at, if the secondary structure of the coil is compromised, in other words, the insulation between each of the coil strands becomes a short or a shunt, not actually a short, but a shunt, you will lose that ringing. If you lose that ringing, what you'll then get is a curved event smoothly from that point there to that point, and you'll also lose burn time. With any fault relative to primary or secondary, the first thing you lose is burn time. So once again, if you reverse that, if burn time's okay, then the amount of energy created is okay. So that predicts coil failure, future coil failure perhaps, because you may have lost the ringing but still have a reasonable amount of energy, but it will fail. So burn time is very important, current in primary, and in our case, coil ringing. Firing line voltage, voltage is pressure, and pressure is on a vertical scale, from ground zero here to that point there. That represents the electrode on the spark plug. The amount of pressure it has to overcome to get the spark from the coil to the plug electrode. Now, we can't, because I can't scale the attenuation of this probe, I also can't scale that measurement. On coil on plug in primary, it should measure 25 volts. That much I can tell you, but I can't scale it with this. So it's not, in our case, that critical because we've got ringing, we've got burn time, we've got current. And you know what? 3 out of 4 pretty much nails it. That is an impeccable pictorial view of this ignition system. What I'd like to do is leave this setup as it is. I'm going to run out of channels, we're pretty full, to look at power supply and ground references now. So I'm going to have to trade in some of these events for the next part of the presentation.